So I started with a simple question. Can I use Godot's built-in features to draw a signed distance field, and then save that result to a texture? Because if you've worked with SDFs before, you know they're incredibly useful, but they're also kind of abstract. You don't really see them in their raw form. You just sample them and hope they're doing what you think they're doing. But here's the thing. Godot's already generating one for you. Every time you use LightOccluder2Ds, there's a signed distance field being built internally for the Godot lighting system. The signed distance, the gradient normals, everything is there. It's just not exposed in a way that's easy to think about, inspect, or reuse. So what we want to do is take that invisible system and make it visible. And not just visible, something we can save, explore, and plug into other shaders later on. Before we get to the code, let's talk about what signed distance fields are. On screen here, you can see a simple shape, a square polygon with 4 boundary edges. But now I'll show the SDF view. This fuzzy gradient you're seeing now, that's the signed distance field. Every pixel in this image is encoding how far it is from the nearest boundary. That's the distance part of the signed distance field. On the inside of the square, these distance values are negative. Outside the boundaries, the distance values are positive. And right on the edge of the shape, that distance is 0. That's the signed part of the signed distance field. Cool, so with just that single value, we'll know how far away any selected pixel is from the shape, and if it's inside or outside of the shape. Another important part of the SDF is how the distance values are changing across the field. You can think of this like a height map, like hills and valleys and slopes. The steepest slope downhill will always lead to the nearest edge or the deepest valley. That direction is called the normal. So now, at any pixel in the SDF, we can get 2 things. How far that pixel is from a shape, and the direction that the pixel needs to move to reach that shape. That's what makes SDFs so useful. They give us important spatial data that we can use for things like smooth text rendering, outlines and glow effects, or even collision detection against shapes and meshes. And later in the video, I'll show how I plan on using this data in my particle simulations. Before we continue, don't forget to like, subscribe, and share the video, especially if you want to see more content like this. Even better, if you know how to use YouTube's hype feature, give us some extra momentum by throwing some hype points our way. We only have 7 days after the video is released to get that hype. It means the world to me, and it's the best way to help us grow the channel. Okay, back to the video. Let's look at what Godot can do with signed distance fields. There are a ton of resources and videos out there about generating signed distance fields, and using their cousins, the signed distance functions. In this video, we'll be focused on the fields and not the functions. If you want to know more about SDFs and how they're constructed from geometry, or more info on using signed distance functions for specific shapes, you should check them out. Luckily, in Godot, we won't need to manually construct the SDF data at all. We'll capture a 2D SDF field that's already baked for us. Of course, we'll need to jump through some hoops to get there. The gist is that in Godot, LightOccluder2D nodes can be made to act like the SDF shape we've been working with, the one that the distance values are built on. And even cooler is that we can combine any number of LightOccluders to contribute to a single merged signed distance field used by the 2D lighting system. It's already built for us, signed, already combined, and already has the normals for us. Less math, nice. It does come with some small trade-offs, which I'll touch on in a bit. But for now, we won't be generating the SDF manually. We'll just be extracting what Godot already computes every frame. Alright, let's get to the fun part, my first SDF Explorer. Let's build a tool to help us visualize and use the built-in signed distance field, step by step. First, we'll set up a subviewport, and use a subviewport container to move it off screen. This is where we'll capture the SDF that Godot creates. We'll set the viewport and container sizes to be 1024 by 1024. This will be the resolution for our SDF texture. The higher it is, the more accurate the SDF will be. You can adjust it as needed as long as you use the same dimensions for everything. Then we need to set a few more properties on the subviewport. First, we need to enable the transparent background in the viewport section. The transparent background flag will let us store alpha transparency into the texture pixels. even though we really don't need it for an SDF. I'm doing this to force the viewport to return a 4-channel RGBA format, instead of just 3 channels in the RGB format. Second, we'll disable 3D on the viewport. Disabling 3D will speed things up since we don't need full 3D here. Next, in the rendering section, we need to check the Use HDR2D option. This high dynamic range setting allows us to store floating point decimals in each channel, instead of values between 0 and 1 like a normal texture. We'll need that to store our SDF data. That's all we really need for the viewport settings, but you could also explore the SDF section for more controls over it. I've oversized the SDF and scaled it up for a smoother field. Next, we'll need the shapes that drive the SDF. I mentioned earlier that Godot uses LightOccluder2Ds to create the SDF data. A LightOccluder2D allows us to have a shape by providing vertex points of a polygon. Creating that shape can be a pain sometimes, so I use a custom auto-occlude polygon tool class to help. It's basically a polygon 2D that automatically generates LightOccluder2Ds underneath it. What's neat about this is that as I edit the polygon in the editor, the LightOccluder updates in real time. Godot also supports multiple shapes in a single SDF. Every LightOccluder2D that has the SDF collision flag enabled will be baked into the data. If this flag is off, that polygon won't contribute to the field at all. So now we can add any number of shapes to the viewport by instantiating the auto-occlude polygon scene. Each polygon can have its own position, scale, and the set of points that makes up the closed shape. But these shapes alone do not give us the SDF. To show the SDF, we need to use a material shader that will do the work for us. So we'll add a color rect that fills the entire 1024 by 1024 viewport and assign this shader to it. This will be our World SDF shader. Its job is to take the raw SDF data and convert it into something we can actually visualize on screen, or write out to a texture image file. Inside this shader, we'll use some of Godot's built-in SDF functions. First, we'll convert from screen UV space into SDF space, using the screen UV to SDF function. Then, at that position, we sample the sign distance with the texture SDF function. And finally, we'll read the surface normal gradient, using the texture SDF normal function. At this point, the distance value and the normal values are all in different ranges, so they're not directly usable for visualization. We'll fix that by remapping everything to a consistent 0 to 1 range in a moment. Before we do that, the shader needs to know the scale of the SDF. We'll reuse the same resolution as before, 1024, and treat that as our working remap range. Now we can pack everything into a color. We'll start by scaling the sign distance by our texture range, giving us a value from -1 to 1. Then we remap that into a 0 to 1 range so it fits cleanly into a color channel, where 0.5 represents the surface boundary. We'll apply that same remapping to the normal X and Y components as well. Finally, we'll store the data into the output color. The signed distance goes into the red channel, the normal's X component goes into the green channel, and the normal's Y component goes into the blue channel. What we end up with is a visual representation of the SDF, where each pixel is encoded with both the distance and the directions, all packed into a single texture. Like we mentioned earlier, Godot already combines all LightOccluders into one field, assuming they have their SDF field flags enabled. The SDF contains each of the shapes automatically, but there's nothing stopping us from modifying the results however we want. And in this case, I want a shader setting that I can turn on and off that will cause the SDF data to include the world edges of the texture as shapes, even if we didn't add polygons for it. You can use this Apply Border Uniform setting to enable world bounds as part of the field, where the world edge constraints are baked in. I have reasons for this, but you might not need it. And you can see how it changes the results when we toggle the setting. This is coming along nicely, but there's one artifact that I want to mention. If you look closely in some regions of the texture, especially the midpoints between two shapes, you'll sometimes notice some unstable normals. This happens when a point is exactly halfway between multiple surfaces. It can also show up near sharp features and corners or due to floating point precision. When it happens, the distance will still be correct, but the normals could point the wrong way or become ambiguous and unreliable. There's a mathy reason why that happens, but it's not a big issue for now, and we can safely ignore it. It's an expected artifact of SDF union operations, and not a bug in our setup. Okay, now that we have the raw data displaying in a viewport off the screen, we can copy that data onto the screen, and start adding some features to probe the pixels to see their values. To do this, we're going to add a texture rect node to the visible part of the screen. We'll copy the texture from our sub-viewport into that texture rect, and add a new material shader to it. First, we need to set the control size to match our 1024 by 1024 resolution like before. Then, we'll add the new shader. This will be our SDF display shader. This shader will expose several toggles that will let us change the way the texture is presented on screen. So we'll have a setting that will make the shapes visible on top of the SDF. We'll have a setting that makes the edges of every border visible or not. We can turn off the SDF itself so we can visualize the shapes and the edges by themselves. And we'll add a flag that will show the SDF in grayscale instead of the colorful version we've been working with. None of these settings change the actual SDF that still exists off screen, but they will let us connect a few UI checkboxes so that we can explore the data in different ways in real time. Like before, we need to make sure we set this shader's range uniform to the same size as our texture, so 1024 in this case. Once the shader is in place, we can overlay the original geometry on top of the SDF, highlight the edges of the shapes, view the raw SDF color data, and switch between color and grayscale. All of these should help us better understand the working parts of the SDF. Now let's add a simple probing tool. We need a way to view the SDF data for any selected pixel in the texture, and then draw a straight line from the mouse cursor to the nearest shape using that data. To do that, we'll use the mouse inputs. Whatever pixel the mouse is over can be sampled, and the values can be printed to screen. So at any given mouse position, we can check the SDF display texture to see the distance value from the red channel, and the normal values from the green and blue channels. We'll print these values to a label so we can view and debug them. I made it so the label can be turned on and off with the control key, but that's not really needed. The only thing missing now is to draw a straight line from the mouse position to the nearest edge. To do that, we need to add another texture rect, whose only job is to display this normal. This second texture rect node will be a child of the first texture rect, and it needs to be that same size 1024 by 1024 resolution like before. The main differences here are that this new node will have its Z order changed to 1, so that it draws on top of the parent texture, and its draw signal will be connected to a GDScript function. This GDScript function is what draws the lines, using the signed distance and the normals that are currently under the mouse cursor. Alright, now we can interactively query the field and see the normal line to the nearest shape edge. Sweet! And here's that same caveat I mentioned earlier. Between multiple equidistant surfaces, the normal direction may be unstable. It's safe to ignore for now. Once everything looks correct and we verify the data using our mouse probing tool, we can also try capturing the original SDF texture to a file. First, we'll set up a hotkey so the user can hit the spacebar to save the file. Then, using that hotkey, we'll call a save screenshot function. All we need to do in this function is grab the texture from our sub-viewport, convert that texture data to image data, and finally call the save EXR or save PNG on the image. I suggest going with EXR as it can hold more precise data. And now, every time we hit the spacebar, the simulation should save the SDF data to a physical image file in the Godot resource folder. For now, it always overwrites the same image file, but we could change that later. You can then copy this file anywhere or use it for any number of purposes like lighting or collision handling. And I just happen to have a very specific use for this in mind, one that I'll dive into in an upcoming video. For now, remember that you can use this texture as sort of a world map. And I'll be using this SDF to give my voids an actual world to live in, with walls and obstacles automatically built in. So don't forget to subscribe if you want to see that video. And that's my first SDF Explorer. It's basically how I taught myself what makes up a signed distance field. and how to intuitively think about what they are under the hood. We started with a question. Can we use Godot's built-in LightOccluder system to actually understand and extract SDF data? And the answer is yes. We're not generating anything new, but we're taking what Godot already computes for its own 2D lighting, exposing and visualizing it using some shaders, and turning that into a reusable texture image. Once it's saved to disk, it's no longer tied to the Godot lighting system at all. It's just useful spatial data, and you can use it almost anywhere. You can find this project in our GitHub repositories if you want to download and try it yourself. The link's in the description. I hope you found this useful. Let me know in the comments if you have other ideas on how this SDF can be used. Thanks for watching the Pathfinder's Codex, and as always, never stop trying new things.